Are you still connected, Captionist? Okay, so it didn't boot you off. Okay, great. Let's skip this slide because there's nothing on it. What's that? Oh, yeah, good point. Good point. The everyone who's here pretty much is not a chemistry major. There might be a few chem engineers here, but a lot of disciplines make people take chemistry because chemistry is about materials, and pretty much every discipline has something to do with materials. Gen Chem sucks in many ways, technical difficulties aside. One of the reasons being that general chemistry serves as a survey of chemistry. And as a result, it seems like a whole bunch of barely connected things because it touches on a whole bunch of different chemistry disciplines. And it seems to sort of hit things and move along, right? There is a context to it, but it really doesn't become clearer until spring when we spend far more time talking about actual chemical reactions, right? But really the underlying unifying theme for chemistry, right, is that we're all about materials, which means molecules. And specifically, there are two parallel branches of material properties we talk about. There's what I refer to as the physical parts of chemistry, right? And so these are in some sense as much physics as chemistry because they're not really about rearranging atoms to make different molecules. They're about what the molecules themselves do when you change the physical systems or the physical parameters of their system. So things like state of matter, whether something's a solid, a liquid, or a gas, is somewhat chemical in nature, but it's not strictly chemical in nature, right? Melting ice to water doesn't require me to do any kind of bond making or breaking. And so it's as much physics as chemistry. And these other properties as well don't require me to do any kind of bond making or breaking, and that is usually the defining characteristics of things that are purely chemical. So things like solubility, if I dissolve something, right, doesn't require me to do anything terribly chemical, but it does create a change in material properties. And we talk a fair bit about that, especially in the fall. Frankly, we spend more time in the spring talking about the actual chemical part of chemistry, right? And so fall is less coherent, I would like to say, than spring, where spring is really all about doing chemistry and talking about reactions, right? And in that case, the questions I ask refer specifically to chemical reactions where I'm rearranging atoms. And so I'm trying to form new substances, right? And those substances form fast or slow, right? This is kinetics, which is a big topic in spring, right? There's a yield of reaction, which is not usually 100% and is connected to the type of reaction and the energetics of the reaction. And so that's kind of the physical chemistry side of things in the spring, right? And number 8 becomes one of my obsessions in the spring if you're still here with us. I don't mean you're necessarily going anywhere, but there's multiple sections of this. You're not necessarily in the same section. But the idea of having more than one reaction happening simultaneously becomes a big theme in the spring once we talk about reactions. And so the idea of having byproducts of reactions becomes a thing. For fall, for a lot of fall, we talk mostly about physical properties, right? More than changes in composition. We spend about 2 weeks talking about actual chemical reactions in the fall, whereas in the spring, we talk for probably 12 or 13 of the 14 weeks about actual chemical changes, right? The distinction is really one of composition, right? So for example, we talked a minute ago about a phase change, right? Boiling water is physical because it's water when you start and it's water when you end. There's no actual change in material composition. Cracking an egg certainly makes the egg look very different and behave very different, but the chemical composition of the underlying materials is unchanged. What's tricky about chemistry in this idea of composition versus change is what you really need to see is the thing that you don't tend to ever see, which is the microscopic picture of what's going on. Right? If you're looking just in terms of properties, steam is really, really different than water. Right? It's a gas, right? You can put your hand through it and barely feel that it's there. It is generally speaking hotter, right? It's not nearly as thirst quenching as water, right? And so it's very, very different, yet it is chemically the same. And the only way you know that it's chemically the same is if you could see the molecules, which you generally speaking can't. As you probably know, water is H2O, 2 hydrogens stuck to an oxygen. Whether it's steam or liquid water, it's 2 hydrogens stuck to an oxygen. Right, and so the picture I need to distinguish between the chemical and the physical is the picture I really never have if I'm in lab holding a substance, right? Ethanol, alcohol, is a liquid that looks a lot like water, feels a lot like water, seems a lot more similar to water than ice or steam in terms of its basic properties. You could pour it, you could mix it, you could wet the desk with it, which is much, much harder to do with steam or ice, right? But it's because they're microscopically identical that steam, water, and ice, right, are the same chemical substance, and it's because they're microscopically different that ethanol, alcohol, and water, right, are chemically different, even though they're physically very similar. And so one of the real challenges, if you're studying chemistry, is to develop some kind of microscopic mental picture, right? The other thing, I'll say it now and emphasize it even more later when we talk about molecules again, the other sort of challenge here is that, much like this picture, even when I show you pictures of the molecules, they tend to be fairly static, right? And the other big thing to remember about molecules is they are always moving. They're trying to sort of imply that with that sort of shadow on the molecules, that those molecules are moving. But a lot of what we need to think about and understand in chemistry is invisible to us, which is part of the challenge of chemistry, right? Here's an actual chemical change, rust, right? And rust is essentially the incorporation of oxygen into a metal matrix. And again, it becomes clearer in the microscopic picture because you can see, whoops, I should not touch this. You can see the atomic difference in the microscopic picture. My red spheres are oxygen atoms. My gold spheres are iron atoms. And in the top picture where I have pure unadulterated iron, there's no oxygen incorporated. After the chemical reaction, I now have iron mixed with oxygen. All right. In this case, there's also something of a physical change, as you've probably noticed if you've ever seen rust. It is a different color than the underlying metal, right? But the big change, again, is compositional, and you only really see it in the microscopic picture, right? The reason they make you come here, even though you're not a chemist, even though many of you resent being here because you don't want to be a chemist, right, is because whatever your discipline, whether it's biology or physics, right, you deal with physical substances, right? And those physical substances are fundamentally molecules. And so if you want to build a bridge, you got to build it out of something, right? And the materials you choose, right, have specific properties, right? And you want to choose them to have the appropriate properties to the function you're trying to do, right? Biologically, life is all about molecules, right? And so one of the things to try to keep in mind, and I'll try to emphasize here, especially in the fall, where there is a certain lack of coherence to our narrative, right, is that what we're really trying to formulate is a series of questions one asks about a material that allows me to determine both the physical properties of the material, which is again a big focus of fall, and ultimately the chemical properties of a material, which is a much bigger property in spring, right? And so we will try to create a sense of coherence, even though if you look at the topics individually, they seem often very, very different, right? In the end, as I like to say, because it makes chemists seem far more important than they are, right? Chemistry is about everything, and I intentionally separate that word, right? Because chemistry is about materials, things are made of materials. And so if you can hold it, touch it, taste it, or smell it, a chemist would care about it, right? In the end, all of these questions fall into one of two categories. They're either fundamentally qualitative, right? What is it? Or it's fundamentally quantitative. How much of it is there? And so we do spend a lot of time dealing with numbers. And for those of you who might be a little number phobic, you might resent the quantitative part of the course, right? But we can't really escape the numbers because this is fundamentally a measurement science, and those measurements, right, are usually numerical, right? But it's not a math course, even though it sometimes seems to be masquerading as one, because our numbers aren't numbers, right? Our numbers are data. And there's a key distinction between the two, right? A number is a number, right? And in math, if it's 5, it's 5, and it doesn't really matter what the 5 represents. What makes it a datum, a piece of data, is that it has a unit. And don't ask me why I always say it 3 times with exclamation points, right? Because the unit is what really makes it a physical science as opposed to a math problem, right? Because the unit gives context to the number, right? And it also makes my number a measurement as opposed to simply a counting exercise, right? 11's a number, right? But if I give you an 11, it does not tell you anything about what that 11 represents, right? And so in here, even though it takes an extra 3 seconds, every number should have a unit associated with it because the unit provides the context to the number. It tells me what it is I measured, right, and what specific unit I used to measure it. So 11 in here should be automatically wrong. Not that I have a red pen that I feel the need to use, right? It's 11 somethings, right? It might be 11 pounds, it might be $11, it might be 11 points, right? But it has to be 11 somethings because it isn't really a math course, right? And the more specific I can make that unit, the better, right? 11 pounds is great, except I still don't know what you threw on the scale, right? And 11 pounds of raisins is very different than an 11-pound baby. Equally delicious, but nonetheless two fundamentally different things. You'll laugh later, right? But 11 pounds of raisins is different than 11 pounds of sand, right? And even 11 pounds of raisins isn't necessarily terribly specific because I don't know where that sand came from. And so frankly, the more specific my unit is, the better. I will spend exactly 5 seconds on this because we don't really care. You probably know from previous science courses that there are these things called SI units, which stands for International System, right? These are, generally speaking, the standard units in physical sciences, right? Also sometimes referred to these days as the metric system, right? We don't necessarily feel the need to be bound by SI units. The only time SI units really matter is that they're internally consistent. So if you're doing a calculation using some kind of algebraic equation, if you use all SI units, you get all SI units out of it. We don't necessarily care. We do care about the units, but they don't have to be SI units necessarily. All right. There are two types of units, again, a distinction worth knowing, but not something we need to do much with, what are known as pure units and derived units. There are really only 4 pure units. Every other unit is derived. And they refer to 4 principal properties of the universe, right? Charge, which is one we don't really deal with in the fall, which is expressed in coulombs. And the ones we do tend to deal with, mass, which is a really big one, expressed in kilograms, which is a measure of the amount of substance, of a substance, length or distance, typically expressed in meters, or a variant, and good old time, typically expressed in seconds. Every other unit is derived from those 4 fundamental units. So for example, a speed is a combination of a distance and time. Meters per second, miles per hour, right? Volume, right, which is something we also frequently measure, is technically distance cubed, right? And so this is what I mean by a derived unit. There's no real bias between a pure unit and derived unit other than the fact that these pure units represent something fundamental in nature, right? Whereas my derived units are combinations of the fundamental. But in the end, whatever the unit is, it should be applied to the number, right? Because for us, all numbers are data. We don't really do math problems, even though it sometimes seems that we do. We do measurements and use those measurements often to try to calculate something else. So there's some math being done, but it's really about the units of measure and what they imply. And so in this sense, right, you know, 4 is 4 is 4 is 4 in a math class. Here I want to make a distinction between a whole bunch of different 4s, right? And in fact, 4 I hate because it has no units, right? Even 4.0 or 4.00, which looks really scientific because, hey, look, it's got a decimal point and everything, right? Doesn't tell me anything, right? I want a unit that tells me what I have 4 of. So 4.00 pounds is now a piece of data. It is also, however, only a partially helpful piece of data because I don't know pounds of what. So pounds of carbon would be different than pounds of raisins. Even that's not terribly specific if I don't know where the sample came from, right? The most helpful unit is the one that's so long that nobody tends to want to write it, right? Which is that I had 4 pounds of carbon that I removed from the brain of a Tyrannosaurus. I now know where the sample came from. It's not just a random carbon sample. It's a specific carbon sample, and so the reader of my report would know where to go to get the sample if they want to reproduce my results. Right. And so the more specific the unit, the better, because it tells the reader, right, what very, very specifically I'm talking about. Right. The other thing, and really the big thing, well, was supposed to be the big thing for today before our technical difficulties, right, is that even the way I write the number, unit aside, tells me something about the data. And so again, in math and on your calculator, there is no distinction between using a 4 and a 4.0. Right? In fact, your calculator, if you just put a 4 into it, will often add as many zeros as it wants, depending on how you have your calculator set. Right? And it doesn't change the math on your calculator to have a 4.00 instead of a 4. However, because I'm writing data, not just numbers, it implies something different about the way the measurement was made. Right? And as many of you probably know, what I'm referring to is significant figures or significant digits. Right? Because I am writing measured numbers, right, I only can record and therefore write digits that I actually measured. And so there's a difference between a 4 and a 4.0, because in the 4.0 I measured 2 digits, whereas the 4 I only measured 1 digit. Right? This is really a implicit statement of the precision of the measurement. Right? I polled, I think this was actually 2 years ago now, and people say all kinds of fun things about significant figures. Some of them are unprintable. Right? And so depending on your background, one of the more interesting ones that people who told me, for example, that in physics, or some people even said chemistry, right, there were always 3 sig figs, right? And so in the answer, you always had 3 sig figs, 2.12, right? The fact is there are rules that apply to sig figs, and you know, they're really, in some sense, more lab rules than lecture rules, because let's face it, I just hand you numbers in here, we don't actually measure them. But implicitly, the numbers I hand you should be representing some real measurement. And therefore, I need to be giving you proper information in those numbers, which means it should have an appropriate unit that tells me what it is I measured. And it should only have digits that represent the actual precision or accuracy of the number measured. And so there's really 2 different precision issues here, right? One refers to sort of old school measurement devices that are literally things with lines on them. And so here's a ruler with lines every 1 inch. Right. The general rule of thumb for a measurement device that has lines on it is that you always have 1 more digit than you have lines, right? Because if I were to measure this block, right, yes, I only have lines every inch, right? But I can see approximately where my block ends between those 2 lines. it's not quite halfway between the second line and the third line. And so I can estimate the tenths of inches, right? And so if I have lines every inch, right, my measurement is good till tenths of inches. If I have lines every tenth of an inch, my measurement is good to hundredths of an inch. All right. And this is really simply a question of your ability to see. If my lines are too close together, right, then this rule falls apart a little bit, right? But as long as I have the ability to see approximately how far I am between the lines, I always have one more digit than I have lines, right? And so for something like that, the fundamental limit on the accuracy is actually half the next decimal position. So if I measure that to 2.4 inches and I write 2.4 inches as my length of the block, right? What I'm really telling you is that it's approximately 2.4 inches. It's not exactly 2.4 inches because of my limited ability to see, right? What I am sure of, if I wrote that, is that it's not 2.3 inches and it's not 2.5 inches, right? But my actual measurement is always a range of values. Because if it was really 2.41 inches, because I don't have the ability to see the hundredths of an inch, right? I mean, here's my block. You would have to have a really well-calibrated eye to tell that that block is 41% of the way between the second and third line. All right. And so my 2.4 inches is really a range of values. What I'm really saying is that block is somewhere between 2.35 inches and 2.45 inches. Because if it was less than 2.35 inches, I would have rounded it down with my eye to 2.3. And if it was 2.45 or more, I would have rounded it with my eye to 2.5. Right. And so implicitly, my significant figures put error bars on my number. Even though I might only write it as a 2.4, right? What I'm really saying is it's somewhere between 2.35 and 2.45, or as you might tend to write it, 2.4 plus or minus 0.05 inches. And so that general scheme of measurement always applies when I have a measurement device that has lines on it, right? Of course, we live in a digital world now. Frequently, the lines have been removed and replaced with fancier measurement devices. I brought this in, but good luck showing it on the Zoom. I'm not going to try to turn the camera on because I'll probably end up turning the microphone off. But, well, if I put this, you can see I have here digital calipers. Right. And so there's not really lines I need to read. It's got a digital scale. Right. In this particular case, if you actually read the back of the scale, good luck, it's small print. Right. I'll read it to you. It says accuracy plus or minus 0.2 millimeters. Right. And if you actually read the front of the scale, it actually measures it to 0.1 millimeters, right? For a non-lined device like my digital calipers, right, the precision is less based on my ability to read the lines because I don't have to read the lines. It's based on the fundamental mechanical accuracy of my fancy device. And so in that case, it's not automatically plus or minus half the digit I didn't measure. Right. It's going to be based on the specific measurement device, right? But our default is, right, if I write a number because I measured certain digits, my precision, unless I know otherwise, like my calipers, right, the limit on my precision is always half the first digit I didn't measure. And this is one of those cases where I want to write on the board, but our fancy split class would just make that confusing, right? So, right, there is now a key distinction for us in measured data between 2.4, 2.40, and 2.400. And really, the sig fig issue is all about the zeros, right? Because no one would argue with me that if I wrote 1, 2, 3, 4, 5, that I must have measured the 1, 2, 3, 4, 5, and that 1, 2, 3, 4, 5 is different than 1, 2, 3, 4, 6. Right? It's the zeros that make a difference, because especially in a calculator-driven world, my calculator does not know or care the difference between 2.40 and 2.400. Right? And so, for the most part, sig figs are easy except for the zeros. Right? Any digit I write is significant, or I wouldn't write it. If I didn't measure it, it would be lying. It would be academic and scientific fraud to write down a number that I didn't measure. The only thing that makes it at all complicated is the zeros, because zeros do a couple of different things, right? I have what are known as trailing zeros, right? And these are the ones that your calculator doesn't know or care about. 1.23 works in your calculator the same as 1.230 or 1.2300, right? But there is no reason for me to write those zeros unless I actually measured them. And so trailing zeros after the decimal point are always significant, simply because there's no other reason for me to write them. All right. Leading zeros are never significant only because I could write as many as I want, and technically I know them, right? If my number is 1, 2, 3, I know there's a 0 in the thousands place, right? My 1, 2, 3 isn't accidentally 2,123 where I just forgot to write the 2,000. I know all those zeros are really zeros. On the other hand, there's an infinite number of them. And so as a result, I don't count them as significant figures, even though I actually know they're zeros. Right? And so those two types of zeros at least always have the same rule. Leading zeros, meaning zeros before the first non-zero number, are never considered significant because there's just an infinite number of them I could write. Trailing zeros after the decimal point are always significant because there's no reason to write them if I didn't measure them, right? The zeros in the middle are always significant. Right? Because if I measured the number before it and I measured the number after it, I must have measured that number also, right? The only ones that are a little ambiguous, right? And really the only complication to my sig figs are trailing zeros before the decimal point. Because in this case, I might not have measured them, right? Because I need them to indicate where the decimal point is, right? 1230 is 1230. If I take the 0 away, it's 123. right? And so I need that 0 to tell me where the decimal point is, even if I didn't measure it, right? And so these are the only problem zeros because they're place marker zeros. They're just telling me where the decimal point is. Okay. And so I will leave you with this thought, and we'll come back on Monday with scientific notation. There are different schemes here. If you read books or go on the internet, some people will say if you put a decimal point there, it makes a 0 significant. Other people will say not. The bottom line is, if I've got a 0 before the decimal point, I have to consider it ambiguous, right? All my editorial rules aside, because there's just no way to know whether I actually measured that number or not. Questions or problems? Okay, I'm going to go to church on Sunday and pray for a technological problem-free Monday. Don't forget the syllabus quiz. The answer is in the email. And again, I will send a reminder, but choose your modality for next week by Saturday night. Have a good weekend.
You too. Thank you.
Thanks.
Thank you.
Thank you, Professor.
Thank you.
Thank you.
Thank you.
Thank you.
Thank you.
Thanks, Professor.
Have a good weekend. Thank you.
Thank you, Professor.
Thank you, Professor.
Yeah, what's up?
Good weekend.